In this video, we're going to be learning about refraction. So if we look at this first picture here, I have a paddle. Now, I look at this, the paddle looks like it's bent. But yet, when we take it out, the paddle is perfectly straight. Why is this? Now, let's look at this second picture here. I have light shining into the prism, but then once it hits the prism, it turns into a rainbow, and the angle leaving the prism is different than the angle entering. Why is this? Well, all of this has to deal with an amazing phenomenon called refraction. So, what is refraction? Refraction is a change in the direction of a wave due to a change in its speed as it passes from one medium to another. Now, let's look at this here. We have a little example, a review. This here is a reflection. So let's say we're looking at this beautiful, clear, still lake, and we're looking at it and our image reflects off and we see our image. Our angle of incidence is always equal to the angle of reflection. But when we're looking at a nice, clear, clean lake, we also know that the light goes through and we could see things at the bottom of the lake. This light will bend now as it enters the water. We have all done this before when we've thrown rocks in and then we go to grab the rocks from the water or grab toys from the water and we miss it. There's a reason why for that, because remember, as light enters different mediums, its speed will change. So if its speed changes, that's what causes this bend. So right here, we have an angle of refraction. If we notice, there's a lot more resistance, we might want to say, between the speed of light, the electromagnetic radiation, from the air to traveling through the water, which will cause it to bend towards the normal. So let's look at an example over here. This guy's looking straight down, which is the normal, which is perpendicular, and he sees the rock at its true position. Here's another example where the guy is looking at an angle. Here, the rock is actually here, but he sees the rock over there. Now, why is that? Well, we know that light changes speed as it changes mediums. So as it changes mediums, it changes speeds, which is going to change our perception. That's why that happens. And different mediums will change it in different ways. Some things will move it towards the normal. Some refractive indexes will move it away from the normal. And we're going to find out more about that in the next slide. So, how light is determined by the index of refraction. So, refractive index is a ratio of comparing the speed of light in a vacuum to the measured speed of light in any given material. So right here, we have our speed of light in a vacuum we're saying is 1. Air is pretty much a vacuum. Most of the time we're going to assume it's 1 as well, air. And then we have ice and so on. As it is going there, the ratio increases because there's more resistance. Think of if we moved our hand in our vacuum very fast, there's no friction resistance. So this is the friction for electromagnetic radiation or light. So mathematically, the refractive index of a medium N can be described as the ratio that compares the speed of light in a vacuum C to the measured speed of light in the medium, which is V. So our N is equal to the speed of light in a vacuum divided by whatever we measured the speed of light in our medium or object. So here we go. When light passes from a medium of high reflective index to one with low refractive index, it is refracted away from the normal line. So if we look at here, we're going from a high refractive index to a low refractive index. So it bends away from the normal. Okay? Here, when light passes from a low to a high, it bends towards the normal. So let's go back to I have an example here with a pencil which kind of confuses us. So to explain refractive index, here I have a jar of water. All right? We have a jar of water, nice here. We have air on top, and then inside my jar I have water. Now we know for a fact that, well, the air is going to produce less resistance than the water to electromagnetic radiation or waves going through it. It's going to be harder to pass with water. Think of it as more friction. And we have done this before. So now, let's take a look at this. I have a pencil here. I'm going to put this in, and look what happens. The pencil bends. Now, it bends away from the normal. The light looks at it. Now, here's a misconception students think of now. They go, well, my eyes are seeing it, so it must be a lower index refraction there because it's coming from the air to the water, then to the pencil. But it's not. Our eyes don't shoot out these magical or electromagnetic radiation constantly. Our eyes are reading the electromagnetic radiation coming from the pencil in the water and coming from the pencil here. So the pencil from the water, it starts off going slower and then it speeds up to us. That is why it looks like, if we look at the refractive index, why it is going towards the plane or away from the normal. Do we kind of get that? And there's an example why, because it's coming from the water to our eyes. Okay, and that's the difference from this. This is constantly fast the whole time. This starts off slow, then it goes the same speed as that once it hits the air. And that's an example of the refractive index. So let's go back to my example on this previous page. Once again here, the light coming in here, it's not bending towards it. That's not what we see. We see the object, the light coming from the object that hits our eyes. Our eyes doesn't shoot off light to hit an object for us to see. What happens is our eyes observe the light coming off the object. That's why it bends. If we look at it, it's actually the rays are going this way to our eyes. They're bending away from the normal. That's why this is less than this. And that's why we see the object there, but yet it's actually here. So this leads us to an interesting question. We know we could find our n value or our refractive index by measuring the speed of light and dividing it by the speed of light in a vacuum. But that's not that easy. How do we measure the speed of light through a piece of glass, some water, and through every little thing, even if they're small? How do we measure that speed of light? It took us forever, remember, to measure the speed of light normally. Well, this is how Snell did it. He first looked at every incident angle and every refraction angle and saw how it was off. Okay, so he was able to measure the angle of incidence and angle of refraction. So he first did this with water. So he did. So then he took the sine of each of these angles. So then he took the sine of each angle of the incidence and the angle of refraction of the water hitting the air hitting the water. And then he plotted this in a graph. So right here, he took all of these angles and put them as sine, and what is their value? So that's my incidence. And then he did my reflection. And from that, he was able to find my slope, which is 1.33. And that there must be my, well, you got it, my refractive index. So that's how we found my refractive index. And now this created Snell's formula, where my refractive index is equal to, if we look at this for whatever object we're going to, it's going to be equal to my incident angle divided by my refracted angle, or my initial angle divided by my second angle, okay? And that becomes very, very important in later calculations. So Snell noticed many things about the refraction of light. He noticed that the wavelength and speed of light also changed as it changed mediums. He also noticed, remember, that frequency does not change. So for electromagnetic radiation, we could have a change in wavelength, we could have a change in velocity, but we cannot have a change of frequency. That is always constant. Now, so right here, we have a relationship. One way I like to remember this is everything I put my initial or my first wavelength or speed, my initial, my incidence on top, and my refraction on the bottom. Everything except for my refractive index. Because remember, this is the ratio of going in versus out. So it's the exact opposite, where everything is going to be going in versus out, where this is going to give me the exact opposite, okay? All right, so here is our first class example. Oops. A ray of yellow light with a wavelength of 570 nanometers travels from air to a diamond at an angle of 30 degrees. Determine the following: the speed of light of the diamond, and B, the wavelength of the light as it travels in the diamond. So this is general Snell's law in general. So let's start off with what we know. We know my wavelength is equal to 5.7 times 10 to the negative 7 meters. Okay, because nanometers means 10 to the negative 9. We also know my angle is equal to 30 degrees. And we're trying to figure out here what is going to be my speed in the diamond. So we want to figure out V2. Now we know my V1 is equal to, we're going to say roughly 3 times 10 to the 8. As we learned before, that's the speed of light in air or a vacuum. Now, if we look on page 667, there's a table there, because most of your questions will tell you the reflective index, unless if you're trying to find it out. So the reflective index of air is 1. It's actually 1.0003, but we're just going to say 1. And we know the reflective index of a diamond is 2.42. So for A, we're going to try and solve this. Basically, here we're looking at velocity. All right, and we're trying to find my V2. So in other words, I'm going to rearrange this. So velocity is equal to, we're going to have V1, N1. Okay, so now when we solve this, we're going to start plugging everything in. I'm going to end up getting 3 times 10 to the 8 meters per second multiplied by 1. And that's going to be all divided by 1.24. Or sorry, 2.42. Which will end up giving me 1.24 times 10 to the 8 meters per second. So that's going to be the velocity for A. That's 2. Okay, now let's try B. So B wants to know what is the wavelength. So I'm going to put N2 over N1 is equal to my wavelength of 1 divided by my wavelength of 2. Here we're trying to find my second one, right? We're trying to find what is my wavelength of 2. So my wavelength of my refractive wavelength is going to be equal to lambda 1 N1 divided by N2. Which is, same thing again, 5.7 times 10 to the negative 7. Divided by 2.42, which is going to end up giving me 235 nanometers. Okay? Let's take a look at my second question now. It says a ray of light passing through water at a speed of 2.26 times 10 to the 8 meters per second enters a piece of glass at an angle of 42 degrees and slows to a speed of 2.8 times 10 to the 8 meters per second. What is the angle of refraction? So I know my incidence velocity is equal to 2.26 times 10 to the 8 meters per second. Okay. I also know my angle of refraction is 42, or my incidence angle is 42. I also know my velocity of refraction is equal to 2 times 10 to the 2 times 10 to the 8 meters per second. Okay. Now, we're trying to figure out what is my angle of refraction. So that's my second one. Okay. So this here is what, make that a question mark, what we're trying to figure out. All right. So we're going to start using Snell's law for this. So I'm going to end up putting down, we have sine 42, or sine theta 1 over sine theta 2 is going to be equal to my velocity of my incidence divided by my velocity of my refraction. We're going to rearrange this, so I'm going to end up getting sine theta 2 is equal to my velocity of my refraction multiplied by my sine of my incidence, all divided by my velocity of my incidence. Alright, so now we end up getting theta 2 is equal to the inverse of sine, and we need all of this part here together, which is going to give me 2 times 10 to the 8 multiplied by sine 42, all divided by 2 times 2.26 times 10 to the 8. And that's going to end up giving me 36.4 degrees. Okay, so now let's take a look at this next question. This next question is a conceptual question. So looking at this question here, it says, these relationships may apply to reflection or refraction. What relationships apply to reflection of a wave from the glass plane? So reflection. So if I look at this, even if we're looking at reflection, if I look at this, my angle of incidence is equal to my angle of reflection. That is true. Is this true for refraction? This is definitely not true for refraction. My angle of incidence isn't always equal to my angle of refraction, because if we have different refractive indexes, my angle of refraction will be different. So then sine of my angle of incidence is equal to sine of my angle of reflection. That is true for reflection, because you're staying in the same medium. But now as soon as we're going in refraction, we're changing mediums, which means my angle is going to be different, so the sine of each angle will be different. Now my wavelength of incidence is equal to my wavelength of refraction. Well, yes, that's true, because if we're staying in the same medium, that means the speed's staying the same, which means my wavelength is staying the same. But if we're going in refraction, we're changing different mediums, which means my velocity slows down or speeds up, causing a change in wavelength. The only thing that doesn't change is refraction. And then number 4, same thing. Change in velocity and reflection is true because you're staying in the same medium, so everything stays the same when you're doing reflection. But in refraction, they do change. So my answer for this is going to be D. So this one here is a very interesting question. So here we're going to have light coming in at an angle of 60 degrees and it's reflected off this mirror here. And it goes like that. Now we know from reflection this has to be 60 degrees. Okay? Now we look at my normal, it goes down like this. So what is the angle based off of this here from here to the 30 degrees? Well, coming off, if it hits and we move this down over here and we have this line here, here's my mirror, it's going to hit right here it's going to hit right here and bounce off at 60 degrees, right? But now I look at this 60 degrees. So we have this here has to be 90 degrees because my normal is always 90. This is 30. This is 60. So then what's going to be this little bit left here? That's 180 minus 30 minus 90 minus 60. Well, that's going to give me 0 degrees. So it's actually going to be right on this line right here at 0 degrees. So the angle between the reflected and the horizontal is actually 0 degrees. It is parallel to it. So in this question it says, when the ray leaves the glass, the horizontal displacement d from the normal is what? So here's my picture. We have glass here, we have a ray coming in at 30 degrees, and then it is entering something obviously with a higher refractive index because it's moving towards the normal. And so there's my D, and what says down right here, there is my refractive index is 1.5, which makes sense. It's moving towards, it's going in this direction. And then as it leaves it, if we look, this right here, it moves away from my normal. So then, once again, this is lower. This must be air here as well, or something less, okay, on the other side. Now, let's look at this here. Let's have an idea of what's happening. So basically, we want to know what is this distance. So I'm going to start off with what we know. We know our refractive index of both air is 1.0. So N1 is equal to 1.0. We know N2, it's actually 1.00003. N2 is equal to 1.5. Okay. What else do we know? We know my angle is 30 degrees. Now, before I can find this distance here, I know this length here, so I want to be able to find out what this angle is. If I could figure out what that angle is, then I could just use simple trig to find out that distance there. If I know this distance, I would know the adjacent, and I know the angle, so then I just use tan to find my opposite. So we want to figure out now what is angle 2 using Snell's law. Okay, so angle 2 is equal to my question mark. So let's try that out here. So I'm going to look at this and I'm going to have sine theta 2 is equal to divided by N2. When I plug all these in, I'm going to get an angle of 19.5 degrees. So now, using this, I could use just simple trig. We know we're trying to find my opposite here. I know my adjacent, and we know my angle. So in this case, I'm going to use tan, which is equal to opposite over adjacent. Okay, so tan is equal to opposite over adjacent. So I'm going to have my adjacent is 1 times 10 to the negative 2, and that's meters, and that's going to be tan 19.5 is equal to my opposite, and that's going to give me a total of 3.5 times 10 to the negative 3 meters is equal to my opposite. So my distance is equal to D. So now that we're done, I want you guys to complete these questions on page 668 and 670.